revision video for GCSE June 2018, the higher tier Unit 2, and it's question 13, and it's all about rounding and significant figures. So here's our question. We're not going to look at that too much to start with. We're going to think about our method though. So we're just going to recap a few things. What are significant figures? How we reverse some rounding that has happened. And then we're going to look at how we find the maximum or minimum, or the greatest or least, depending on the question, in a calculation. So let's go away and look at these three things, and then we'll put it all together to figure out this exam question. Okay, so let's remind ourselves. The first step that we want to review is what are significant figures. So we've got three examples, one about the number of atoms that's been calculated, one about how long it took a computer to process an answer in seconds, very small number, and then the average age of year 11 in years. So first of all, we're going to round all of these to one significant figure. So I like to think of one significant figure as basically being as lazy as you can. So if I was to represent this number the laziest way I could, I would probably say, oh, it's 200,000. And that's because I'm taking the first digit. That's important. That's the one I want to keep. I only want one significant number in my answer, but I do have to check next door to see if I need to round it up or not. And it's a 3, so I know I don't need to round up. I have to have these zeros afterwards to keep the place value, because remember, if these 5 zeros weren't there, it would just be 2. And 2 is not an accurate representation of the number of atoms, but 200,000 is far more accurate than 2. The time to process this computer to one significant figure, I'm going to keep these zeros at the beginning, and my first significant figure I'm going to look at is this 3. I'm going to check next door, see if I need to round up, but it's only a 4, so I don't. So I'll keep my zeros and my 3, and everything else will disappear in the rounding process. Remember, if these zeros disappear, 0.3 seconds compared to 0.0003 seconds is much, much slower. So these zeros are really important in keeping this figure as close to it is as possible. If we look at the average age of year 11 students to one significant figure, I want to keep this first one here, or the value in this column. But I look next door and see if I need to round up, and because it's a 5, I do need to round up. So 15 to one significant figure is going to become 20, or 15.763842 is going to become 20 to one significant figure. So you can see that when we're talking about ages, certainly in this situation, one significant figure isn't a great representation of how old year 11s are. Okay, let's have a look at all of these to two significant figures. And you can see in this one I've kept the 2, but the second digit has become a 4. And if we look back at the original number, because the next column over, the third column, is a 9, I know I need to round this 4 up 1, round the 3 up 1 to become 24. So I've got 240,000. And remember, we've got all of these zeros keeping that place value. If I don't want to make this 24, I need to keep it in the right columns to keep the value as good as it can be. The next one, I'm going to keep 2 digits, so I'm looking to keep the 3 and the 4 are going to be the ones that are interested in my answer, but I have a look next door, and because it's a 9, this 4 is going to become a 5. So to two significant figures, we should have 0.00035. And then for year 11s, I'm keeping the 1 and the 5, and I just have a little check into the next column, it's a 7, so I am going to have to round that 5 up. So we've got 16 years. Let's quickly do 3 significant figures. 1, 2, 3, because the next column is 2. I don't need to round up, so I've got 239,000 atoms. And this one, 1, 2, 3, the next number is a 3, so I don't need to do anything to that 9. So I've got 0.00349, and then for this age, 1, 5, 7, and then my first 3 digits that are of interest, or my first 3 significant figures. And so the 6, have a quick look at the 6. Because it's a 6, I know I need to round up, so it's become 15.8 years. So the next part of our thinking process was to reverse, or think about reversing this rounding process. And we're trying to find the upper and the lower bounds of all of these figures. So we know that they've been rounded. What could this number have been between. And we're just looking, the upper and the lower bounds are the cut-off points between it rounding to something else. Okay, so 200,000 was the number of atoms to one significant figure. What could it have been between? Imagine we don't know what that number was. What could it have been between? All we know is that it was rounded to one significant figure. So this 2 was the important number. That means it could have been anywhere between 150,000 and 250,000. And if you think about any number in between those 2 points, it would round to 200,000 to one significant figure. So what we're kind of doing is we're jumping from that 2 and we're looking at that next column, and I need to go 5 above and 5 below, or in this case 50,000 above and 50,000 below. And I could write it as an inequality if I wanted to. The second one, 0.0003 seconds. And again, to find my upper and my lower bound, I'm going to jump into the next column and add or subtract 5. So in this case, it would be 0.0005 of a second that I need to subtract or add on to get my upper and my lower bounds. And again, I could write that as an inequality. And if I look at the 20 years, which have been rounded to one significant figure, if that's all I knew, I didn't actually know the age of those people in year 11, but just knew it was 20 years to one significant figure, then my lower bound would be 15 and my upper bound would be 25. Anywhere between 15 and 25 is going to round to 20. And this is my cutoff value, 15 at the bottom end and 25 at the top end. Okay. So just I went into the next column, basically took off 5 years and added 5 years on. And there's an inequality. If we have a look at two significant figures, very similar process, we're just one column over. So I'm now looking, in this case, after the 4. So I need to take 5,000 off and add 5,000 on to give me 235,000 and 245,000 from a lower bounds. The next one, the 3, the 5, I need to look in the next column over, add 5 on and take 5 off. So it would be really, it would be 0.00005 of a second to subtract and to add on to get your upper and your lower bounds. You may just be able to see what's going on and not have to think about adding or subtracting or taking away too much. You may just be able to spot some patterns. 16 years to two significant figures. So I'm going to look into the next column, which will be first column after the decimal point, so my tenths. So 15.5 or 16.5, adding or subtracting on half a year. Let's whiz through three significant figures then. 238,500 and 239,500 for my upper and my lower bounds there. So 238,500, 239,500. Again, going into the last column or the next column after this 9, so I'm going to have 8,5 on the end and 9,5 on the end. Think carefully about where those numbers sit. And the last one, 15.8 years, I need to go into my hundredths column and be looking at 0.75 and 0.85 for my upper and my lower bounds there. There they all are. You can have a quick look at all of them. Okay, next bit. Okay, so now we're going to have a look at finding the greatest or the least value, the maximum or the minimum, when we are doing a calculation. And this is what we're building towards in this exam question that we're looking at. So in these 4 calculations, 40 has been rounded to one significant figure and 170 has been rounded to two significant figures. And we've got an addition, a subtraction, a multiplication and a dividing to have a look at. And for both of these calculations, or for all of these calculations, we are going to find the greatest possible value that this could have been and the least possible value that this could have been. There's maybe where you want to make some notes because there's some good things to get your head around. So if I want to make this addition as big as possible, I need to think about what 40 could have been. So before I get too stuck in, I'm just going to think, well, 40 to one significant figure could be somewhere between 35 and 45. So then my upper and my lower bounds for 40. And whilst I'm there, I'm going to think about 170. And 170 to two significant figures could be somewhere between 165 and 175. And it's a good idea to have these jotted down somewhere near your question so you can use them as you go through. So if I want to make this answer as big as possible, I'm going to use 45 here and I'm going to use 175 here. So this question could have been, or the greatest value of this addition could be 45 plus 175, so the upper bound plus the upper bound. If I wanted to make this addition as small as possible, you might have spotted it already, I'm going to do 35 plus 165, so the lower bound plus the lower bound. I'm not going to actually bother working them out here, but we're just going to talk about which bounds you need. To make this subtraction have the biggest possible answer, I'm going to start with the biggest number and I'm going to take away the smallest. So I'm going to start with my upper bound and I'm going to take away my smallest, so my lower bound. So I do upper, take away the lower, and that will give me the biggest possible answer. To get the least, I'm going to start with the smallest and take away the most, because remember we're thinking about getting the least of the final answer. So this time I do the lower, take away the upper. So when we do subtraction, we have to think a bit more about what's going on. Multiplication or multiplying again isn't too bad. To make this number the biggest possible, I'm going to have the biggest, the upper bound for both. So upper times upper, and to get the least, the lower times the lower. When we do dividing, it's worth having a bit of a think about this to the side. So I often think of 2/10 compared to 3/10, and I can see 3/10 will be the biggest fraction out of these two. So I know I need to get the biggest number in the numerator. And in the denominator, which of these fractions will be the biggest? A third is bigger than a quarter, so I need the smallest denominator. So 3/10 is bigger than 2/10, so that reminds me that I need the biggest numerator. But a third of a cake is bigger than a quarter of a cake, so that reminds me I need the smallest denominator. So I need the biggest number on top, so the upper bound on top, and the lower bound underneath, so upper divided by lower. And if I want to get the smallest, the least value for the calculation, I go back and I have a think. I want 2/10, so I want the lowest, the lower bound on the top, but to make it as small as possible, I need the biggest denominator. So in this case, I'm going to have the lower divided by the upper. So it's important that you're clear on these. You don't necessarily need to write down lower divided by upper, but you need to be clear that I need the smallest value divided by the biggest value to get my answer. So now we're going to put those steps together and deal with the exam question. We've been given three values, A, B and C, all correct to two significant figures, a formula to pop them into, and we're asked to calculate the least possible value when we do this calculation, and we need to show our working. So the first thing I do when I'm doing one of these questions, I write all of these down and I write down the upper and the lower bound, acknowledging that these are done to two significant figures. So 27 is somewhere between 26.5 and 27.5. 1.9 somewhere between 1.85 and 1.95. And 0.81 somewhere between 0.805 and 0.815. Now I've got those, I can start thinking about the formula. And it's worth thinking about the last thing we just looked at on the previous slide, that to get the least value from the division, I need the smallest on the top and the biggest on the bottom. So I want the smallest numerator and the biggest denominator. So the biggest denominator isn't too tricky. Let's deal with the numerator to start with. I've got a subtraction now that I want to make as small as possible. So to make this as small as possible, I'm going to do the lower of A, take away the upper bound of B. So in this case, 26.5 minus the 1.95. So the lowest value for A, take away the biggest value for B. And I've already decided I need the biggest value for C, so I'm going to divide that by 0.815. Pop that into my calculator and maybe just give it to two significant figures if you see fit. So the tricky part of this question is making these decisions, whether you want the smallest or the biggest, and how you arrive on whether you the smallest or the biggest value. So just take time to think those through. So let's have a look at an alternative question where we're given a bit of context. So we've got a set of ornaments that's being made from a piece of wood which is 2.5 meters long, and that's been measured to two significant figures. The carpenter removes 0.45 meters, correct to two significant figures, of damaged wood from the end of the piece. She then splits the wood equally into pieces 0.3 meters long, correct to one significant figure. And the two questions: what is the most amount of ornaments the carpenter could make? Show your working. And what's the fewest amounts of ornaments the carpenter could make? So let's have a look at this problem. If this is my piece of wood measured to 2.5 meters, well, before we go any further, we know that's only correct to two significant figures. So in fact, this figure could be actually anywhere between 2.45 and 2.55. The carpenter is then going to cut off 0.45 from the end. So we start with the full block there. I'll chop that bit off the end. But that bit is 0.45. But again, that's a rounding or a rounded figure. That could be anywhere between 0.445 and 0.455. Once they've chopped that end bit off, they're then going to divide this equally into pieces that are 0.3 meters long, or as many pieces they could get into that are 0.3 meters long. So they're just going to chop off these sections, as many as they can, to make these ornaments. So if each of these we know is going to be measured to 0.3, well, that's only to one significant figure. We know that could be somewhere between 0.25 and 0.35. So it's important we've got these upper and lower bounds for each cut or each measurement that we're going to use. So we think about that, what the carpenter is doing there, starting with the total length, they're taking away the cutoff, and then they're dividing by the piece length, 0.3 if you like, to get how many bits they're going to make. So if we want to make the most, I need to start with the longest bit of wood. So I need to start with my upper bound. And if I want to make the most, then I'm going to cut off the minimum amount of waste. So I'll cut off the lower bound. Then if I want to make the most ornaments, I want to make them as small as possible to fit as many in here as I can. So I'll make them 0.25. So to make the most, I'm going to start with the upper bound. I'm going to cut off the lower bound, and then each piece I will cut into as small as possible bit. So I'm going to do upper to lower divided by lower. So 2.55 minus 0.445 divided by 0.25, and pop that into your calculator and you get 8.42. Now remember, these are ornaments, so that would only be 8 ornaments. Couldn't have 9, could only have 8. So let's have a look at the fewest amount of ornaments they could make. And it's going to be a similar process. The fewest amounts of ornaments would be if we have the smallest bit of wood to start, so the lower bound, and I cut off the most, got rid of the biggest bit of damaged wood from the end, and then I made the ornaments out of the biggest sections possible. So the fewest will start with the lowest bound for the length, take away the upper bound for the offcut, divided by the upper bound for each of the pieces. So again, pop your numbers in for that, pop it into your calculator, and you get out that could just be 5.7 ornaments, but we can't make 0.7 an ornament, so it would have to be 5 ornaments. So very similar to the exam question in terms of the calculations and what you've got to do, but just disguised in a bit of context. So just look out for things like that. And that is the end of this GCSE video. I hope that was helpful.